Hello, good evening. Welcome to the fifth week of the problem solving session for this course, Availability and Management of Groundwater Resources. So today we'll be solving some questions that is related to porosity, permeability, transmissivity, and storage coefficient. Hello. Okay, and this will be based on the content of the week 5 lectures. And as usual, I'll be posting some questions and you can put in your answers in the chat box, and then we'll go into the explanation of the solution. Good evening, Danish. So we'll move on to the question discussion. You can put in your answers in the chat box, and then we'll slowly move on to the solution. So the first question is this one: what is the relationship between transmissibility and permeability for an aquifer of depth D? Here transmissibility is represented by T, permeability is represented by K, and the depth of the aquifer by D. Yes, Danish, the correct answer is option B, T is equal to K into D. So let's just see what all are the terms that is coming in this expression transmissibility. So two of the terms that are coming in transmissibility is the permeability and the depth of the aquifer. So permeability, we have seen in the earlier classes also, it is a property of the soil which is making it easier for water to flow through it. And this flow of water is occurring through pores, and not just through pores, through interconnected pores. So if the soil or the aquifer material is such that the pore interconnectivity is good, then the ease with which water will flow through the media will be better. So what is happening when the soil is permeable? The void spaces or the pore spaces are continuous in nature, and it is allowing water to pass through the mass. And when the soil is impermeable, like that of clay, even though if there are pores, the interconnectivity between the pores will be not that good, because of which it will not be able to transfer water properly through it. So this is the property permeability, and we also saw in the last class when it came to the Darcy's equation that permeability is represented by a term called hydraulic conductivity, and hydraulic conductivity is represented with the letter K. Now transmissivity is nothing but it is when you consider a small volume of the porous media to quantify what is the capability of transmitting water, then this term is described as the transmissivity. So as you can see here, a small representative volume of the porous media is taken, then the ease with which water can flow through it is represented by transmissivity. So if permeability is a property, transmissivity is quantifying the capacity with which the water can be transmitted through it. So transmittivity is defined as a product of the hydraulic conductivity and the thickness of the saturated aquifer. And although we see that in the question, the thickness is represented by D, it can also be represented by B. So do not get confused with any other dimension of the aquifer. It is always going to be the thickness of the aquifer multiplied by the hydraulic conductivity. Transmissivity will be product of the hydraulic conductivity into thickness of the aquifer. And you can see the unit will be in the dimensions of L square by T. So if the unit will be meter square by second or meter square per day generally. So here you can say there are two conditions that are compared: hydraulic conductivity of 100 meter per day and thickness is 10 meter. Then we get the transmissibility as 1000 meter square per day. And for another aquifer whose conductivity is less but the thickness is more, again the transmissibility is more. So this is why the small representative portion of the aquifer is coming into play over here, because we can see that the thickness is varying, which is actually increasing the transmissivity in both the cases, although the hydraulic conductivity is less in the second case when compared to the first case. So that was about transmissibility. Now let's move on to the next question. The coefficient of permeability indicates the ease with which water can flow through a soil mass. The soil type which has less permeability out of the following is which one? Is it gravelly soil, clayey soil, sandy soil, or both sandy and gravelly soil? Danesh, maybe think about it once again and then say we are talking about the soil which has less permeability. Yeah, right. So here again, what soil type will not allow water to transmit through it very easily. So the first option, gravelly soil. First option, gravelly and sandy soils are examples of aquifers. And aquifers have good permeability property. Both sandy and gravelly soils are good aquifer, but clay soil is not a good aquifer because, like I said, it's very it doesn't, the interconnectivity between pore spaces is not very great when it comes to clay soil, so it is less permeable. Now, storage coefficient has the dimension of what out of this following? Will it be in units of meter square or centimeter square, or meter cube or centimeter cube, or will it be in the units of meter or centimeter, or is it going to be dimensions? Right? So the answer is dimensionless. So just let's see what the storage coefficient is and how it is being dimensionless. So you can see over here that storage coefficient is the volume of the water that is removed from an unit area of aquifer for unit drop of hydraulic head. So when a unit area of aquifer is taken and there's one unit drop of hydraulic head, whatever is the volume of water that is collected is the storativity. Now this, when it comes to the unconfined aquifer, will be as a picture that is shown on the left side, and for the confined aquifer, it will be as how it happens in the right side. Now let's see how the unit is being how is it being dimensionless. So you can see here, just a second, you can see that the definition of storativity is the volume of water per unit area per unit hydraulic head. So it will be meter cube per meter square per meter. So meter cube per meter square per meter, everything will get cancelled and it will become equal to 1. So this is why this parameter, storage coefficient or storativity, is said to be dimensionless. So that was the answer for the earlier question. The storage coefficient has a dimension of, it doesn't have a dimension, it's dimensionless because all the units are getting cancelled because of its definition. Now, next question. What does porosity refer to? Is it the shape of the particles, sorting of the particles, percentage of pore spaces in a material, or is it the percentage of cement in a material? Right, Danish? It is a percentage of pore space in a material. So, as you can see here, porosity is the measure of the void spaces in a substance, which is defined as the ratio of the volume of the pore spaces in the soil material to the total volume of the solid substance. Now, total volume of the solid substance will consist of the volume of the solid particles as well as the volume of the pores. So the total volume of the solid particles is going to be the volume of the pore spaces as well as the volume of the solid particles. So a ratio of this expressed in percentage is called the porosity. Now there's another quantity called the void ratio, which is giving us the ratio of the volume of the pore spaces, volume of the pores to the volume of the solids. If porosity is taking into consideration the total volume of the solids, that is total volume of the soil, here void ratio is taking into consideration the volume of the solids, the soil particles. So that is another property which is linked to porosity, because the E is equal to the volume of the pores divided by the volume of the soil particles, whereas here porosity is equal to volume of the pores by the total volume of the solids, soil, which will also include the volume of the solids. Pore spaces and void spaces are the same. Voids, when they say void or pores, it's just the empty space in between the solid packing of the soil particles. Next question. Porosity is independent of which of the following parameter? It's of which of the parameter? Is it independent of particle shape, packing, sorting, or hardness? Correct. So porosity is independent of this property hardness, whereas it is dependent on particle shape, packing, and sorting. So porosity, let's see what the shape, packing, and sorting is. So you can see here, when the solid particles are loosely packed, it will look like this. When it is closely packed, it will look like this. That is what they call it, what they mean when they say that it is dependent on the packing of the particles. Now sorting of the particles is, you can see that there is larger soil particles, then again there is smaller soil particles. So how all these different sized solid particles are packed together is what it means when they say that sorting of the particles. Then shape of the particles, we know some of the particles will be rounded, some will be angular. So this is what they mean when they say that the porosity is dependent on the shape of the particle. So let's remember that porosity is dependent on three major factors: the shape of the particle, the packing of the particle, how closely packed it is, how loosely packed it is, and also the sorting of the particles. So the answer for that question, hardness is not a criteria on which porosity depends on. The sixth question, water flows through permeable materials faster than impermeable materials. Is this true or false? Correct. Water does flow faster through permeable materials than impermeable materials. This doesn't need much explanation. The correct answer is option A. Seventh question, a soil sample with a large amount of spaces between the particles, what will they be? Soil with high porosity, low permeability, high capillarity, or low infiltration rate? Correct, it is soil particles with high porosity. We studied about how water can go through soil particles which are larger pore spaces. So soils with a large amount of space in between them, like gravels, when they are together, are called soils with high porosity. Now, eighth question, if a rock is compressed and its volume decreases, how will the rock's density and porosity be affected? They're giving a condition, the rock is compressed and the volume is decreasing. So how will this rock's density and porosity be affected? Okay, so correct option, it's density will increase and porosity will decrease. So let's see why. Density we know is the mass by volume. So here they are saying that the volume is decreasing. So as the volume decreases, density is going to increase. Now when density increases, porosity, when the material is compressed, the pore spaces are going to get reduced because its volume is decreasing. The volume of the pores is also contributing to the total volume of the rock. So when the volume decreases, the pore space is also decreases. As a result of which, the porosity is going to decrease. So the correct answer for this option is option C. For this question is option C. Density is going to increase and the porosity is going to decrease. The value of bulk modulus of compression for plastic clay lies in the range of. Okay. So these are just some numbers which we'll have to keep in mind. There's no other way to learn this. The correct answer is 5 to 40 Newton per meter square. So let's see where this is relevant. So when it comes to the storativity or the storage coefficient of confined aquifers, it is here that bulk modulus of compression of the plastic material or the bulk modulus of compression of clay comes into role. So this equation by Jacob is giving us a equation for the storage coefficient of storage, where it is a product of the unit weight of water into the thickness of the aquifer into alpha plus porosity into beta. Now here we know gamma W is the unit weight of water, which is 9,810 Newton per meter cube. B is the thickness of the aquifer, the saturated thickness of the aquifer. Alpha is, you can see, reciprocal of the bulk modulus of elasticity. So bulk modulus is nothing but it's the measure of the ability of a substance to withstand change in the volume when it is under compression. So when a material is being compressed, how much is its ability to not change its volume when the force of compression is exerted on it is what is defined as its bulk modulus. And bulk modulus of elasticity is characterizing the compressibility of fluid, how a unit volume of fluid can be changed when pressure is working upon it and it is made to compress. So here they have said, according to this equation, gamma W B into alpha plus N beta. Here alpha is the reciprocal of the bulk modulus of elasticity of the aquifer skeleton. Aquifer is composed of if the aquifer is composed of the material, then we need to know what is the bulk modulus of compressibility or bulk modulus of elasticity of that material. Find the reciprocal of it and then use it in that equation. It is here that this bulk modulus of compression and elasticity is coming into significance. Similarly, beta is the reciprocal of the bulk modulus of elasticity of water, which is 2.1 into 10 to the power 9 Newton per meter square. This is erroneous here, it is Newton per meter square. So let's just go through it once again. For a confined aquifer, in order to find the coefficient of storage or storativity, it is a person named Jacob had given this equation that is relating it to the elasticity, bulk modulus of elasticity of water and the aquifer material, and is given by this expression. And in this expression, alpha and beta is representing the reciprocals of the bulk modulus of elasticity of water and of the aquifer skeleton and water respectively. And there are values for different types of material. For plastic clay, it is 5 to 40 Newton per meter square. In 5 to 40 into 10 to the power 5 Newton per meter square. Then for stiff clay, it is 40 to 80. For different types of material, this is how the bulk modulus of compression is. These are available in the lecture materials that has been provided. So you can go through that also if you want to. I just took the table and used it over here. Next question. An aquifer is having 622-meter thickness and the hydraulic conductivity is 2 into 10 to the power minus 6 meter per second. What will be the transmissivity in meter square per day? This is a very simple numerical. You can do it and put in the answers in the chat box. We did go through what is the equation of transmissivity. How is transmissivity represented? All the values have been given in this. We just have to do the math. Correct, Danish. The answer is C. So let's go to the solution. So we know that transmissivity is T equal to the product of the hydraulic conductivity and the thickness of the aquifer. So thickness here is given as 622 meter and hydraulic conductivity is given as 2 into 10 to the power minus 6 meter per second. The options over here for transmissivity is given in meter square per day. So we just have to be careful about it is a direct substitution into the formula. We just have to be careful about the data conversion from seconds to day. So multiplying 622 into 2 into 10 to the power minus 6 and converting the seconds into day by multiplying with 3600 into 24, we'll get the answer 107.48 meter square per day. So this is a simple numerical that can come and you can expect a lot of such simple using simple applications of the formulas during your exam also. Okay, so which of the following will be the void ratio of the soil if the porosity of the soil is 22%? So void ratio, I had explained earlier, it is the volume of the voids to the volume of the solids, and porosity is the ratio of volume of voids to the total volume of the soil. Now, porosity and void ratio are linked in the following way. If E is the void ratio and N is the porosity, E is equal to N by 1 minus N and N is equal to E by 1 plus E. So this is how these two terms are linked with each other, are related to each other. So using one of these relations, we can find out the solution for this question. Correct? Yes, it's option. So option C. So the porosity is given as 22%, which is equal to 0.22. We saw the relation between E and N as E is equal to N by 1 minus N. So using that relation over here, we'll substitute 0.22 divided by 1 minus 0.22, which is equal to 0.28. So again, this is one category of simple numericals that can come. Next, which of the following is the degree of saturation for a fully saturated soil sample? So before going into the numerical, degree of saturation is nothing but the volume of the water present in the soil material to the volume of the voids. So we saw what porosity is, we saw what void ratio is. Now degree of saturation is what is the volume of water to the volume of voids. Comparing the volume of water to the volume of voids is what is called the degree of saturation. So what will happen if a soil is fully saturated is a question over here. What might be the degree of saturation for a fully saturated soil sample? Okay, so the correct answer is 1. So what happens when the degree of saturation, to the degree of saturation when the soil gets fully saturated is the volume of voids is going to be equal to the volume of water, because when under conditions of complete saturation, all the void spaces are going to be filled with water. So the volume of voids and the volume of water is going to be equal. So it will be it will cancel out and it will be equal to 1. So the correct answer is 1. Now, what happens if the degree of saturation will be equal to 0 for a perfectly dry sample? Is the statement true or false? Right? So we just saw what is the definition of degree of saturation. Degree of saturation is nothing but the volume of water to the volume of voids. So when it is fully filled with water, the volume of water and volume of voids is equal to be the same. When it has no water, the volume of water is going to be equal to 0, which is making the degree of saturation also equal to 0. So the degree of saturation is equal to 0 for a perfectly dry sample. The statement is true. Moving on to the next question. Which of the following gives a relationship between porosity and void ratio? Okay, so this is not a direct question. Just hold on a second. I didn't provide the solved solution also for this. Okay. So let's see how we are getting the answer for this question. So we said the porosity is the ratio of volume of voids to the total volume, and it is related to void ratio in this way. Now we did a numerical where E is equal to N by 1 minus N is equal to E by 1 plus E. But none of the options here is giving that, but instead this option is given. So if you solve this, you will get, one second. Yeah, you solve this, you will get this 1 minus N is equal to 1 by 1 plus C. When you take, when you bring 1 by 1 plus C to the left hand side and take N to the right hand side, it will become 1 plus E, no, 1 minus 1, wait. Yeah, 1 plus E, 1 minus N, yeah, it will be 1 plus E minus 1 is equal to N by 1 plus E. Sorry for the horrible handwriting, but I can only manage this in the screen. So this one will get cancelled and you will get N is equal to E by 1 plus E. So when I post the slides, I will do the solution part for this and also post it. Yes. So if we know either of this one relation, we'll be able to get the other. So we know E is equal to N by 1 minus N. So if we can substitute that here also, we'll be able to get this, or just learn these two by heart. Okay. So the question for the answer for this question is option B. By making use of these relations, we'll be able to get that this option is the right answer. Now the porosity of a soil sample whose void ratio is 0.35 will be what? Again, making use of that relation, so you will have to solve it. Correct. It's option C. Let's see how it is solved. So by this relation, N is equal to E by 1 plus E. So E is given as 0.35. So direct substitution 0.35 into 1 plus 0.35. Sorry, 0.35 divided by 1 plus 0.35. I forgot to put one division over here. I correct it right away. Okay. And then when you do the division of 0.35 by 1.35, you'll get 0.259. And since porosity is expressed in percentage, multiplying it by 100 will give you 25.9, which is option C. Moving on to the next question. What is the fraction of total porosity available for a fluid flow called as? Okay. So let's see what the correct answer is. So what is effective porosity? Effective porosity is nothing but the total porosity. Out of the total porosity, what portion of the pore volume is available for the fluid to flow is what is called the effective porosity. So volume of water available to circulate in porous media by the total volume of the porous medium will give us what is the effective porosity. Now, another name for effective porosity is called kinematic porosity. So here the question was, what is the fraction of the total porosity available for fluid flow called as? It's effective porosity, and also another term used for is the kinematic porosity. So the option D will be the correct answer, both A and B. So once again, effective porosity is nothing but what portion of the total porous volume is available for the fluid to flow is called as the effective porosity. Moving on to question 17. What is the other name for hydraulic conductivity? Correct, it's coefficient of permeability. This we had seen in previous as well as today also we had discussed about permeability. The correct answer is option B. Now I'll be discussing some questions from assignment 3 and assignment 4. Some key questions that requires a little bit of explanation. Everything else is very similar to whatever problems that we had already discussed in the problem solving sessions. So let's move on to that. Is there any doubt regarding whatever sample questions that we discussed today?
Hello, madam, audible?
Hello?
Madam, am I audible?
Yes, yes.
Madam, in the difference in the slide you have shown for void ratio and porosity, can you go to that slide, madam? I think second or that slide.
Just a second. This one.
Yes, madam.
Yeah. What about this one?
Yeah, here it is. The first one, porosity, is defined as ratio of volume of pore spaces to the
To the total
total
volume.
volume of solid substances. In
Yes.
void ratio also, it is a ratio of volume of
Okay.
void spaces to the total volume of solid
Right.
substances. There is
This
no
this
difference.
this is wrong. Actually, porosity is not the total volume of the solid substance. It's the total volume of the soil, not solid
Okay, okay,
substance.
okay.
What
It's
is
clear, madam.
provided here is wrong.
Okay, madam. Thank you.
So shall we move on to the assignment 3 discussion? Okay. So moving on, the third question in the assignment 3 was which instrument is used to measure soil moisture percentage? And the correct answer is tensiometer. So let's look into what the other options are. Piezometer is an instrument used for measuring pressure. We had learned about the potentiometric surface and piezometric surface. So piezometers are devices which are inserted to check the pressure, particularly of the confined aquifers. Hydrometer is an instrument used for measuring the density or specific gravity of the liquid. And barometer is an instrument that is used for measuring the atmospheric pressure. And tensiometers, this is how a tensiometer is, and it is inserted into the soil, and how there is a porous tip and water is sucked into it, and then there's a vacuum gauge that will measure the tension that is generated by the vacuum over here. We don't have to go into the details, but I just wanted you to have a look at how the instrument looks like. Okay. Now question 7, which model is commonly used to assess aquifer vulnerability by considering parameters like depth to water table, hydraulic conductivity and net recharge? In the last discussion, there was a doubt regarding the possibility of the model HYDRIS. So let's see what all the models are used for simulating. HYDRIS is one model that can simulate water, solute, and heat transport one-dimensionally, two-dimensionally, or three-dimensionally through variably saturated media. And WQI model is a water quality index model, which is used to quantify the quality parameters of surface water. Drastic model is the answer over here, and here they have particularly mentioned aquifer vulnerability, and drastic model has been developed for the purpose of groundwater vulnerability assessment. So this was where HYDRIS doesn't have a chance. Here HYDRIS has not been developed for the purpose of vulnerability assessment. We can quantify the water transport occurring in a soil medium, but here drastic model is a model that is developed with the intention of a vulnerability assessment of groundwater, and it is including majorly 7 hydrogeological parameters, which is depth to the water, net recharge, what is the aquifer media, what is the soil media, the topography of the land, what is the impact of Vadose zone, and hydraulic conductivity. So this question had specifically mentioned assess the aquifer vulnerability by considering parameters like depth to water table, hydraulic conductivity, and net recharge. Here, HYDRIS model, I'm not sure if it is considering net recharge. We can give boundary conditions, but then I'm not very sure if it is having accessibility to net recharge as an input parameter. The other model that has been discussed in this question is SWMM model. The full form is Stormwater Management Model, and it is for as assessment of storm water runoff, what is for every kinds of sewers, combined sewers, sanitary sewers, stormwater sewers, drainage system, etc. It is a model that has been developed for the analysis and design of stormwater infrastructure. So those were only the two questions that required maybe a bit of a discussion. Then moving on to assignment 4, there's this question number 4. Which type of aquifer is more susceptible to contamination from surface pollution? Danesh, what do you think the answer is? Okay, so the options given here is confined aquifers with a hydraulic conductivity of so and so. Confined aquifers are not susceptible to contamination from surface pollution because confined aquifers are having confining layers, which is not going to allow the movement of these contaminants into it. So option A and D are not at all possible. Now, the doubt is between option B and C. Here they have mentioned it is unconfined aquifer with a hydraulic conductivity of 0.02 and unconfined aquifer with a hydraulic conductivity of 0.1. So when we compare the type of aquifer, confined and unconfined aquifer, the possibility, the susceptibility of an aquifer to contamination is more when it comes to unconfined aquifer in comparison to confined aquifer. But when hydraulic conductivity is considered again, it is more likely that an aquifer with higher hydraulic conductivity will allow the pollutant to get transported through the media better than a soil media whose hydraulic conductivity is less. So although the answer in this assignment provided is B, which I am a little doubtful about, I would also appreciate inputs on the possibility of the answer being B. But as far as my understanding is concerned, I feel the option C is the right answer. Unconfined aquifer with a hydraulic conductivity of 0.1. So there was a bit doubt. I had a bit of a doubt regarding this question. So that's why I thought I'll discuss this. So if you can get a clarity on this from your side also, please do post it in the forum, or you can discuss in the next class. I will also try to get a hold of more clarity when it comes to this question. Then rest are numericals. We'll again go through all these numericals once again. Here the hydraulic gradient of an aquifer is given. If the hydraulic conductivity of the aquifer is 10 meter per day, what is going to be the velocity of groundwater flow through aquifer? So according to Darcy's equation, the velocity of groundwater flow through an aquifer is given by the product of its hydraulic conductivity and hydraulic gradient. Hydraulic gradient is given as 0.005. So multiplying that with K, 10 meter per day, will give us 0.05 meter per day. The options over here is varying in terms of the unit as well as value. So whenever you choose the answer, be careful about the unit also. So here 0.05 meters per day is the answer. So as you see, there's another option with 0.05 meter per hour. So please be sure that we don't go and choose that option. Always be careful of the unit that is being used. Hi Santosh, welcome to the session. Now the sixth question in the assignment 4 was about the rocks that are considered as good aquifers. Now the options provided here is granites and schist, sandstones and conglomerates, fractured limestone and basalts, and volcanic rocks and clay. So we know option A and D are not a possible material for good aquifers, because granite is again in igneous rock, volcanic rocks also come under igneous rocks, clay is an impermeable substance, so it is not forming an aquifer. But again, there is another option, sandstone and conglomerates, which is also a sedimentary rock, which also form good aquifers. But the option is C, fractured limestone and basalts. So again, when I look through, Sandstone and conglomerates. Sandstone is a rock that is formed when grains are compacted together, and conglomerate is when rounded pebbles and sands are held together. That is the difference between a sandstone and conglomerate. So these are also good aquifers, but when it comes to when you compare a sandstone and a fractured limestone, limestone and basalts are the better aquifers, because since limestone is a soluble, it can get dissolved because of by the water that is flowing through it. It is forming a more better aquifer when compared to sandstones and conglomerates. And also limestones tend to have fractures in between them apart from the pores. So these fractures are going to create pathways, better pathways for water movement and storage than the pore spaces in between sandstones and conglomerates. So that is why it is option C in here. So you can refer to the explanation of what sand. If we know what sandstone and all these rocks are, we'll have a better idea for questions like these. Next is again a numerical based on the Darcy's equation. So a confined aquifer having a hydraulic conductivity of 5 meter per day and hydraulic gradient of 0.003. They're asking us what would be the groundwater flow through an aquifer, assuming the area is 100 meters square. So in the earlier question, we made use of the formula V is equal to K into I, whereas in this, we'll have to make use of the discharge value. So we'll be multiplying a cross-sectional area with K into I, because we all know that V is equal to Q by A. So Q will be equal to velocity into A. Velocity is equal to K into I. So Q will be equal to K into I into A. So K is given as 5 meter per day, I is given as 0.003, A is given as 100 meter square. Directly multiplying it, we'll get 1.5 meter cube per day. Also here also, let's be careful about the units. They can always give the hydraulic conductivity in terms of meter per second or centimeter per second or whatever. And we shouldn't always make the mistake of directly substituting it without bothering about the unit and then finding out the answer. So that was question 7. Now question 8. A catchment area of 20 kilometers square has an annual rainfall of 900 mm with sandy soil content of 20% and temperature of 16 degrees Celsius. The groundwater recharge has to be estimated using the Bhattacharya formula. This is the Bhattacharya formula where precipitation is equal to 3.7 into R minus 38 the whole power 0.4. We have no other go but then learn this formula by heart. It is an empirical formula, I believe. So P is representing the rainfall penetration, and R is the annual rainfall, and P is the rainfall that is being penetrated into the soil. So here they have given us the area 20 kilometers square, annual rainfall R value as 900 mm, and sandy soil content 20%. Bhattacharya formula, P is equal to 900 mm, 90 centimeter. Okay. Rainfall is equal to R, sandy soil 20%, 90. Okay, so here what they have done is they have taken the rainfall penetration as well as the annual rainfall as the same. So if there is no other value provided, you can assume both of the values to be the same. I don't see any other explanation for it. Also, when it is empirical formulas, you should be careful of the units. All units are not going to be uniform. Sometimes in some empirical formulas. So here the rainfall penetration as well as the annual rainfall is in centimeters. So what is given here is in 900 mm converted to 90 centimeters and substitute P and R as both the same values. That is what has been done over here. Since there's no another value for penetration that is provided. So 90 is equal to 3. Oh, sorry. Groundwater recharge has been asked. So you're supposed to find P. This part is wrong. Again, let me correct it over here. This is not right. P is not equal to 900. R is annual rainfall is 900 and we have to find P. So 3.47 into 90 minus 38, the whole power 0.4 is giving us 16.855 centimeter, which is equal to 168.85. And since it is nearest to this option, B option, they have selected this as the option. And this question is a little very ambiguous, but Madam, can you discuss question number 4? Okay, 1 second. Let me get done with this and then I'll go back to question 4. So in this Bhattacharya formula, they are making use of this equation P equal to 3.47 into R minus 38 the whole power 4. R, P is the amount of groundwater recharge. R is the annual rainfall occurring. So we have to find P in this question. R value is given as 900 mm. 900 mm is equal to 95 centimeter. And directly substituting into this, you are getting 16.855 centimeters, which when converted to millimeters is 168.85. But none of the options here is 168.85. So it is the option that is nearest to this value. You can choose that option as the answer, which is 135.19, option B. Question 9 in the assignment 4 is what is transmissivity? The rate at which water moves downwards the surface water to the groundwater. Is it the ratio of the fluid flow volume to the total volume of the porous media? Is it combined effects of porous medium and fluid properties? Rate at which water is transmitted through a unit width of the aquifer under a unit hydraulic gradient. So we know that transmissivity is equal to product of the hydraulic conductivity and the thickness of the aquifer. So here they are saying the thickness or the width of the aquifer is 1. Hydraulic gradient is 1. Again, this question also is a bit doubtful because here they're talking about hydraulic gradient and not hydraulic conductivity. This option should have been hydraulic conductivity. But again, none of the other options are relating to the transmissivity term. So based on that, you could have chosen the option D. Again, this question is a little ambiguous. The correct term here should have been hydraulic conductivity, not hydraulic gradient.
Madam, I think it is correct, madam, because we say T is equal to K into
K into the thickness of the
B, yeah,
aquifer.
thickness. Okay, madam. Right.
So through a unit width of the aquifer, say that it's what they mean. The thickness is what they mean when they say unit width of the aquifer. Right, it is correct. I'll say how. So we know that V is equal to K into I. So if the hydraulic gradient is 1, then the velocity is equal to the hydraulic conductivity. So here they're saying the rate at which the water is transmitted through a unit width, again it is related, but then I don't think so. It is a very clear option. Anyways, this is also something you can maybe post it in the forum or because the questions are not being set by me. For more, if you need more clarity, this can be discussed in the forum. So that's for today's session. If there's any doubt regarding all the questions, just okay. Danesh wanted question number 4. Yes, it's this, right? So in this question, they're asking which aquifer is more susceptible to contamination from surface pollution. So we know that confined aquifer doesn't get polluted as much as a unconfined aquifer can get polluted. Why? Because unconfined aquifer doesn't have any confining layer at its top. So whatever pollutants are passing through the soil can reach the groundwater easily when it comes to unconfined aquifer. So when it comes to confined and unconfined, unconfined aquifer is more susceptible to contamination from surface pollution than compared to confined aquifers. Now, let's go to the second term, which is talking about the hydraulic conductivity. When a soil has higher hydraulic conductivity, it means that soil is capable of transmitting water more easily. So if the hydraulic conductivity is less, the soil with the more hydraulic conductivity is going to be um, transmitting the pollutants more easily than the soil with lesser hydraulic conductivity. So that is why I feel option C is the right answer. But again, in the key, it is given as option B. So this was also a very ambiguous question, which I thought maybe required discussion. And since there aren't a lot of people for a constructive discussion, anyone seeing the video and going through the slides can post it in the forum or get to know more about it. So if there's an if there's any doubt regarding again the assignment questions of 3 and 4 or the sample questions that we discussed, please feel free to ask. Otherwise, we'll end this session for today. Yes, Ganesh, sandstones and conglomerates are also good aquifers. But when you compare sandstones and conglomerates to fractured limestones are better than sandstones. If you're comparing any, if you're only comparing granites with sandstone aquifers are aquifers. Granites are not at all aquifers. But when you're comparing the aquifers in sedimentary rocks itself, sandstones are a little less better than limestone aquifers. Thank you, Danish. Thank you, Danish. Wish you the same. Thank you for attending the session and have a great weekend. Yes, so for this problem, I think this could be an explanation. We know that velocity is equal to product of hydraulic conductivity into hydraulic gradient. So when hydraulic gradient is equal to 1, the hydraulic conductivity is equal to the velocity of groundwater flow, or the rate at which the groundwater is transmitted to the rate at which water is transmitted to the groundwater. Now again, transmissibility is equal to product of hydraulic conductivity and depth. Since D is equal to 1 and K is equal to the velocity, transmissibility can be the rate at which water is transmitted. So this could be an explanation, which I just right. So that will be for today. We'll see you in the next week with the questions, the problem solving session for week 6 based on questions on assignment 6. So thank you for attending today's session, and have a great weekend. Bye.